All right, everybody, welcome back. We're going to speak about regression, about trying to build a model that incorporates a prediction of a continuous value. So, let's take a look. Oh, I should say, right, there's various ways to do regressions. Simple regression is exactly what you think of, where we're fitting a line of a y given an x. But there can be multiple regression, where we're trying to fit a value y. Sorry, that was a terrible drawing. A value y given something like multiple x's. That is my terrible attempt to draw 3 dimensions, where what we're trying to fit is something that looks like a plane inside this 3D space. So the multiple dimension generalization of a line is a plane, right? And so that is multiple regression, where we have multiple input values, x1, x2, etc., however many x's we have, and we're trying to predict a single y, or vice versa. We have multiple y's we're trying to predict given multiple x's even. All right, that was maybe a little too much right there at the beginning, so feel free to ignore that, because you don't even know what regression is yet, maybe. So, linear regression is used for looking at a relationship between an independent variable, that's our x there, right? And a dependent variable, that's our y. And you've seen this before, right? So we're going to drop a line in, an equation of a line, which fits this data best. Okay? So whatever this best fitting line is that we are supposed to be seeing, the exact nature of what best means is a topic for another course. But you, of course, just need to know that there's a way to do that, to put a line in so that the overall distance summed up between each one of these data points and the line is the smallest possible number, that all of those distances summed together gets as small as it possibly can get. And that's what it means by a best fitting line. Okay, so this green thing here is a best fitting line. That red thing is a terrible fitting line. This is not a good fit, right? That's not a good fit. What we want is we want the line which minimizes the total error, the total residuals off here, like we were talking about. Okay? So this line that we're fitting, this line is a model of the data. We're saying that this mathematical representation is going to describe the process that gave us these x's and these y's, whatever that process is, right? So it's independent of the data. You can throw that data away and you have this line that you fit from the data. And this line represents whatever made that data. So if we got new data, then we would then, if we got new data, then we would expect it to look similar to the old data, okay? And we would expect this line, this model, to be just as good a description of this new data we've never seen. Right. So this mathematical representation of the data is called a model, okay? What does this model tell us? Well, it can tell us how we expect the process to work. But clearly a line is maybe a simplification. Maybe this line is not the right thing. Maybe this data would be better fit by something that was a little curvy. Okay? So the line may be the wrong model. I don't know. We would have to do a lot of investigating and do some experiments to try to figure that out. But the point of this quote by the famous statistician George Box is that all models are wrong. There's no such thing as the correct model, okay? It's just that we are looking for a model which is good enough, right? We're looking for a model which is useful. We want a model which is, as George said, importantly wrong. It is inappropriate to be concerned about mice when there are tigers abroad, right? And since all models are potentially wrong, we should maybe prefer, in this example, the Occam's razor. We should prefer the simplest possible description, right? And rather than going whole hog into something which has got a lot of bells and whistles. So the point of all this is that when we're building models, we know we're throwing away data and information. And we're doing that to try to get at the heart of the truth, right? To put it in terms, if you're more of an arts person, right? You know, fiction reveals the truth, right? We know that the exact nature of what happens in a novel is not true, but yet the novel is written to represent an experience that resonates with many, many people. Okay? So that's the idea of a model. Another way to think about it is this, right? I forget if I've already told this story to you. I've told it to my other class, I think, not to you. There's a famous novel writer from the 20th century, very early, called Luis Borges. And he wrote a bunch of short stories that were very bizarre. And one of them is about a king who gets given a gift of a map of his kingdom, which is so incredibly perfect in every detail that captures every little nook and cranny of the kingdom. Every blade of grass, everything in the kingdom is on this map. The problem is, in order to capture all that detail, the map has to be just as big as the kingdom itself, which makes it a rather useless object. So, that is the deal. That is why we make models. We make models because we know that we cannot carry around a map as big as the kingdom. We need to simplify in order to understand. All right, that was some highfalutin philosophy. I apologize for that digression. That wasn't really in the plan, but it's something near and dear to my own heart. So models are wrong, but we want models to be usefully wrong. Okay? All right, so let's look at some examples of regression where we try to fit something that might be too simple, a line, onto some data. So we mentioned previously that we have this idea that maybe students' grades are related to their absences, that a student who is very absent quite a lot of the time is maybe going to have a lower grade than students who are much better at attending lectures. All right? So the linear regression can be used to determine whether a change in one variable is related to the change in the other. Right? So if you see this line, it tells you if this is a good fit or not. Okay? And not just whether the fit is good, which is about the spread here, but also whether the relationship is interesting or not, right? Maybe we would get something, if the data was different, maybe we would get a line where there was a relationship with absences, but the slope is so tiny that we hardly care. It makes almost no difference to a student's grade if they're absent or not. So in that case, we wouldn't care about the relationship. But if instead we have this green line, right, where there is a strong relationship, where the more absences definitely affect the student's grade, then we may actually want to try to do an intervention to prevent absences, right? So this magnitude of the effect, this effect size, which is determined by the slope here of the line, right? Rise over run, for those of you that are remembering your high school geometry, right? The slope of the line is a measure of the model's effect size. So this effect size can be estimated, as we said, using the slope of the line. This is, nobody cares about that relationship, all right? We don't care about the independent variable in that case. So remember that things can be positive or negative, right? So this is a highly positive effect size. This is a highly negative effect size. This is a barely positive effect size. And this one is a, oh, my shoulder, barely negative effect size, right? So the slope's magnitude, the slope's absolute value, is what matters in determining effect size. The positive and the negative component just tell you which direction the relationship is. Just like with correlation coefficient, okay? So the effect size, the slope of the line, has nothing to do with the spread of the data, right? The correlation coefficient measures the spread of the data, right? If it's just a circular blob, the correlation is 0. If it's a tight, perfect line, the correlation is 1. So this also is not just the correlation coefficient, but it's also something called the standard error. Okay, we're going to talk more about the standard error here. So the closer the points are to the regression line, the less uncertain we are about our estimate. All right. So we need to make certain kinds of assumptions about our data to be able to fit a linear regression to it. Okay? So we need to assume that the data is linear, right? That there is a linear relationship there. If we think it's a nonlinear relationship, then we shouldn't be fitting a line, right? We have to assume normality of the data, that each individual measurement should be distributed as a bell-shaped curve. We can't have collinearity, which is where a bunch of the variables are all just combinations of each other. No autocorrelation and no homoscedasticity. No homoscedasticity, right? Autocorrelation means that the value at time t is not related to the value at time t plus 1. Okay? And homoscedasticity, well, it's easier to show you in a graph. Okay? So let's talk about these. So this data is clearly not linear. Do not use linear regression. I think that's a pretty open and shut case. Right? If we're doing multiple regression where we have x's and y's, right, then we have to have a Gaussian for each one of these. So if we are just doing a single variable, then that variable has to be Gaussian. If we're doing multiple variables, all the variables have to be Gaussian, right? You have to have that nice bell-shaped curve, and something which is, you know, bell-shaped in y and bell-shaped in x produces a spherical Gaussian there, right? It's Gaussian in both directions, x and y, and together the plane defined by xy makes a spherical Gaussian, a circle, essentially, of the distribution, right? So if your data don't look like this, don't use linear regression. Okay, we assume no multicollinearity. This happens when independent variables are too correlated with each other. Basically, if you have, say, 3 different inputs, and one of them, x3, is actually just x1 plus x2, then linear regression is going to fail, fail, fail. Okay? So autocorrelation can't be in there. So autocorrelation occurs when observations are not independent with each other, right? If you look here, like for this time, these times in here, the Apple stock price is all roughly the same, okay? And over here, it's all roughly the same. And there seems to be maybe even be something like a periodicity in this signal, right? So all those things where you have runs of mostly similar, or if you have periodic things, those are examples of autocorrelation, where the value at time t is related to the value at time t plus 1. Okay? Those things are bad. They break linear regression. Now, note that while the stock price itself is autocorrelated, the day-on-day gains are not. So this is what a time series looks like that's not autocorrelated, right? It looks jaggedy, raggedy. There's no like runs that day 1 and day 2 are very similar, right? There's no clear view of periodicity here. So this is an interesting feature of many time series, and definitely what's used in a lot of time series analysis, which is whereas like where the stock price is today is fairly similar to where it was yesterday, the day-on-day gains, how much you get at each day difference goes up or down, right? Each day we go a little bit up or a little bit down, right? Those are not autocorrelated. This stuff is largely autocorrelation free. All right. So homoscedasticity. Is a distribution homoscedastic? Well, what does that mean? It means this. Do you see how the variability around the line of regression is pretty much constant until you get to here? At that point, the variability blows way, way up. So if at every point along the line, if the variability is pretty much roughly the same, then that is a homoscedastic distribution. If at some point on the line it blows up or it gets really narrow around the line, then that is not. Then we don't have that condition. If the variability changes from one end of x to the other end of x, then you break linear regression. Okay? So let's go with an example here. Does poverty percentage affect the teen birth rate? Right? This is our question. Is there some relationship here? Well, we can try to address this question by regressing teen birth rate on the poverty levels. Okay? So what do you think? Do you think that there is no relationship, a positive one, where increasing poverty yields an increasing teen birth rate? Or do you think that there's a negative relationship where decreasing poverty leads to an increased birth rate? Have a think. Well, here's some data. Let's take a look at it. So we can see here the percent poverty in a state and its birth rate in teen births per 100,000. So let's take a look at the data. First, we need to do our descriptive statistics. We need to make sure we can do a regression. So this is the distribution of poverty percentage over all states. It looks like a skewed normal distribution, but it looks like it's probably a normal distribution with a bit of a lean in it, not something crazy. So it so happens that linear regression is okay-ish with mildly skewed distribution, so I'm not going to reject it based on that. So also true of teen births. All right, when we plot the two against each other, poverty percentage and teen birth rate, I see something that could maybe be a line of regression in there. It doesn't necessarily look curved or anything like that, right? I mean, it seems like it's plausible by my eyeball meter that this could be a line. Okay? So it seems like we have everything we need. We don't, if we're going to imagine the line here, we don't really see great changes in variability. It seems like maybe it is homoscedastic. It seems like there's not a autocorrelation problem here because this is not a time series. There's no multicollinearity because there's no multiple variables. And we've seen that each one of those individual variables is normal. Okay? So it seems like this is an excellent candidate for fitting a line. So we do. Here is that line. So the regression line is the model. This is our hypothesis to explain the relationship between poverty percentage and birth rate. And as you may note, the slope is a positive one. So we're saying there's a positive relationship. An increase in poverty means an increase in birth rate. Okay? The magnitude of this relationship is measured as the slope, right, which we're calling beta. And the effect size, it says this: for every 1% increase in the poverty percentage, we get a 2% increase in the teen birth rate. So, but the question is that a good estimate? We have an estimate. It's the line slope. But, you know, random stuff is random. Is this a good measure of the effect size? For that, we need to look at what I was talking about earlier, the standard error. Okay? So this is our line of regression right here, right? And this shaded gray area around it, these are all plausible results we would get if we got a brand new sample of teen birth rate and poverty. Okay? So inside that gray area, the true line could be this one, or it could be that one. Any line which lies within the shaded gray area is within the standard error. What we're saying is the slope is 2 plus or minus 0.3. So it could be as high as 2.33, and it could be as low as 1.73. Okay? And so this standard error measure is a lot like correlation coefficient, right? That essentially the more spread out, like if the dots that we regressed on were giantly spread out, we would have a big standard error. And if the dots that we're regressing on were quite tight around the line, we would have a small standard error. And likewise, we would have a big correlation coefficient for the blue dots and a small correlation coefficient for the purple dots. Okay. So that is, again, the effect size, how much we care about an effect is the slope. How good the line's fit is, that is the standard error or correlation coefficient, Pearson R or something. All right. So let's look at another example, advertising and sales. Do we have a relationship? Let's get some data. Here is a column of your sales data. Here is a column of the advertising spent. Okay, maybe these are just like companies here. I'm going to say companies. I didn't really think about this. So this is company A, this is B, this is C, ... So is there a relationship between the advertising levels spent and the sales levels spent? Well, let's say we find one, we regress something, and it turns out that the effect size is 23 million. So what does that mean? Take a moment, take a look at each one of these elements, right? A, B, C, and D. Does one of these describe what the slope of 23 million means, what the effect size of 23 million? So what's the X variable? It's advertising, right? What's the Y variable? Sales. Okay, so each increase in advertising dollar leads to an increase of sales. This is the independent, and this is the dependent variable, which is dependent on the value of the independent variable. Okay, so given that description, for every 1 million of euros spent on advertising, we should see a 23 million increase in sales. And that, my friends, is answer A. Okay? So, that's all I had for you on the lovely field of regression. I will see you again on the flip side for our lecture on confounding.